Right now, as you watch this, you are not touching anything. Not the chair you're sitting in, not the floor beneath your feet, not even the clothes on your body. You have never, in your entire life, touched a single thing. And neither has anyone else, ever. Now, before you think I've gone completely crazy, let me tell you something even stranger. This isn't philosophy. This isn't some trick with words. This is physics. Hard, cold, testable physics. And by the end of this little talk, you're going to understand exactly why the universe has arranged things so that nothing can touch anything else. And I think you're going to find it absolutely delightful. But wait, it gets better. Not only have you never touched anything, but you've never even come close. The gap between you and everything you've ever touched is about 100 millionth of a centimeter. That sounds small, but at the atomic scale, it's enormous. It's a chasm, an unbridgeable void that has separated you from every object, every person, every surface you have ever encountered. And yet, somehow, you feel things. You feel the weight of a book in your hands. You feel the texture of fabric. You feel the warmth of another person's skin. How can that be if you're not actually touching anything? That's the puzzle. And solving it is going to take us on a journey through electromagnetism, quantum mechanics, and the very nature of matter itself. Let's start with something simple, really simple. Put your hand on a table. Go ahead, really do it if you have one nearby. Feel that solid resistance, that feeling of contact. The sensation that your hand has met the wood and can go no further. Now, what's actually happening there? If I asked most people, they'd say something like this. The atoms in my hand are bumping into the atoms in the table. My stuff is hitting their stuff. Contact. Simple. But this is wrong. Completely, fundamentally wrong. And proving it wrong is going to require us to think very carefully about what an atom actually is. Now, you've probably seen pictures of atoms in school, little diagrams with a ball in the middle and smaller balls going around it in circles, like a tiny solar system. The sun is the nucleus, the planets are the electrons, and that's that. This picture is useful. I won't say it's worthless. It helped Bohr and others figure out some important things about how atoms absorb and emit light. But for understanding what we're talking about today, it's very misleading, because it makes you think atoms have surfaces, hard little boundaries where one atom ends and space begins. They don't. Let me tell you what an atom is really like, and I want you to picture this carefully. An atom has a nucleus in the center. That's where almost all the mass is. Protons and neutrons packed together incredibly tightly. If you took all the nuclei from all the atoms in your body and pushed them together, the whole thing would fit in a space smaller than a grain of sand. That's how dense nuclear matter is. But that nucleus is tiny, unbelievably tiny. If I blew up a hydrogen atom so that the nucleus was the size of a marble, just a little glass marble you could hold between your fingers, do you know how big the atom would be? Do you know where the electron would be found? A quarter of a mile away, maybe half a mile. The electron would be buzzing around somewhere out there while the marble sits in the center. And in between, nothing. Emptiness, vacuum. Now here's the thing. That electron isn't really a little ball orbiting at that distance. That's the old picture, and it's wrong. The electron is more like a cloud, a fuzzy smear of probability that surrounds the nucleus. It doesn't have a definite position until you measure it. It's spread out over this whole region, doing whatever electrons do, being in a kind of superposition of everywhere at once. But here's what matters for us. That cloud is negatively charged. The whole thing. The nucleus is positive because of the protons. The electron cloud is negative. And the atom as a whole is electrically neutral because the positive and negative balance out. Now, multiply this by every atom in your hand, every atom in the table, trillions upon trillions of tiny nuclei, each one surrounded by its own fuzzy electron cloud. And between those nuclei, emptiness, vast relative emptiness. If atoms are mostly empty space, and your hand is made of atoms, and the table is made of atoms, then both your hand and the table are mostly empty space. So here's the question that should be bothering you. Why doesn't your hand just pass right through? Why can't the emptiness in your hand just slide through the emptiness in the table like two swarms of gnats passing through each other? This is where the magic happens. This is where we discover what solid really means. You see, those electron clouds I mentioned, they're negatively charged, all of them. Every atom you've ever encountered has a negative cloud around the outside. And what happens when you bring two negative charges close together? They repel. They push each other away. You've felt this with magnets. Take two magnets and try to push the same poles together, north against north, south against south. You feel that springy resistance, that invisible force pushing back against your hands. The magnets never meet. They refuse to touch. The closer you try to push them, the harder they fight back. That's exactly what's happening when you put your hand on a table. The electron clouds of your skin atoms are approaching the electron clouds of the table atoms, and as they get close, the electromagnetic repulsion kicks in. Negative pushes against negative. The closer they get, the stronger the push. And they never actually meet. That feeling of solidity, that sensation of contact, it's electromagnetic repulsion. It's force fields pushing against force fields. Your hand is floating above the table, held up by invisible electrical forces, and the gap between them never closes. Let me give you an analogy that might help. Imagine two very powerful fire hoses, big industrial ones, the kind firefighters use. Now point them at each other, water blasting out of each one, the two streams meeting in the middle. What happens when you try to push those hoses closer together? You feel resistance, tremendous resistance. The water is pushing back against itself. The pressure builds the closer you get. But is the water from one hose touching the water from the other? Well, there's some interaction in the middle, sure. But the main thing you experience is the push, the force, the pressure. Electron clouds are like that. When your hand approaches the table, the clouds start interacting. They push against each other, and that push is what you feel. Or try this analogy. Have you ever rubbed a balloon on your sweater and then tried to stick it to another balloon you've rubbed the same way? They repel. They slide away from each other. They both picked up negative charge, and negative refuses to get close to negative. Your hand and the table are doing the same thing, just with trillions of atoms, all at once, all pushing against each other in a coordinated electromagnetic rebellion against contact. Now let me pause here and make absolutely sure this is clear. If I had to explain this to a bright 12-year-old, here's what I'd say. Everything is made of tiny things called atoms. Atoms have a small positive center and a big negative cloud around the outside. When you push two things together, the negative clouds get close to each other. But negative pushes away from negative, so the things can't actually meet. They just push against each other without ever really touching. That feeling of touching, it's just electrical pushing. That's it. That's the core idea. Everything else is details. But oh, what wonderful details they are. Let's deal with a mistake now. A very common mistake that almost everyone makes when they first learn about atoms. Most people, if they picture atoms at all, picture them as tiny little balls, perfect little spheres, like incredibly small marbles, solid through and through. And when you touch something, your marbles bump into the table's marbles, click, clack, contact. This picture is totally wrong. And it's wrong in a way that matters. An atom does not have a hard surface. There is no boundary where the atom ends and empty space begins. The electron cloud just fades out gradually as you get farther from the nucleus. It gets thinner and thinner, less and less probable, but there's no sharp edge. This is crucial. If atoms really were solid balls, then in principle, you could get them to touch. You could push hard enough and eventually, clunk, surfaces would meet. You'd make contact. But electron clouds don't have surfaces to meet. They're fuzzy. They interpenetrate a tiny bit at the edges, and then the repulsion takes over. The harder you push, the stronger the repulsion grows. There's no final contact point because there's no surface in the first place. It's like asking where a fog bank ends. You can walk into a fog and it gets thicker and thicker, but you can't point to a wall of fog. It's gradual. Electron clouds are gradual too. So this idea that atoms are like tiny billiard balls clicking against each other is completely misleading. What actually happens is that their probability clouds start to overlap, the electromagnetic repulsion goes up, and equilibrium is reached. Forces balance, but surfaces never meet because there are no surfaces. Now here's a question that might have occurred to you. If atoms are mostly empty space, and they never actually touch each other, then what's stopping you from walking through a wall? Really, think about it. A wall is mostly emptiness. You are mostly emptiness. Why can't you just pass through like a ghost? I'll tell you why. And it comes down to two things, working together. The first thing is the electromagnetic repulsion we've already talked about. When you push against a wall, the electron clouds in your hand push against the electron clouds in the wall. The force is enormous. At everyday scales, you can't generate enough push to overcome it. But there's something deeper going on too, something quantum mechanical. And this is one of the strangest and most beautiful things in all of physics. It's called the Pauli exclusion principle. Wolfgang Pauli figured this out in the 1,920 seconds, and he got a Nobel Prize for it, and he deserved every bit of it. Here's what he discovered. Electrons are a type of particle called fermions, and fermions have a very peculiar property. Two of them cannot be in the same quantum state at the same time. They refuse. It's not just that they don't like to be together. It's that the laws of physics literally forbid it. Now, what does quantum state mean? It's a combination of things, where the electron is, what energy it has, and something called spin, which is a kind of intrinsic angular momentum. If two electrons have the same position, the same energy, and the same spin, they're in the same state. And Pauli's principle says that can't happen. What does this mean for touching? When you try to push your hand into a wall, you're trying to push the electrons in your hand into the same region of space as the electrons in the wall. But those electrons already occupy certain quantum states. And if your electrons try to move in, they'd have to take on states that are already taken. They can't. The exclusion principle forbids it. So what happens instead? The electrons that are being squeezed have to take on higher and higher energy states. They have to move faster, vibrate more intensely, do whatever they can to avoid having the same quantum numbers as the electrons already there. And those high-energy electrons push outward. They create a kind of pressure. It's called degeneracy pressure, and it has nothing to do with morality. It's purely quantum mechanical. This is the same force that holds up a white dwarf star. When a star like our sun runs out of fuel, it collapses under its own gravity. It shrinks and shrinks. You might think it would collapse all the way down to nothing, but it doesn't. It stops. Why? Because the electrons inside get squeezed so close together that the Pauli exclusion principle kicks in. The electrons can't all be in the same low energy states. Some have to be in higher states. And those higher energy electrons push back against gravity itself. The star reaches equilibrium, a white dwarf, about the size of the Earth, but with the mass of the sun, incredibly dense, and held up by nothing but electrons refusing to be in the same quantum state. That same physics is happening when you push your hand against a table. On a much smaller scale, but the same principle. The electrons in your hand cannot share states with the electrons in the table. They push back. They resist compression. So you've got electromagnetic repulsion and Pauli exclusion both working together, both saying no, both preventing your hand from passing through solid matter. And that's why, even though you're mostly empty space, you can't walk through walls. Now I want to take you on a journey, a thought experiment. We're going to shrink ourselves down, way down, to the size of an atom. And we're going to watch what happens when a finger presses against a table. Ready? Here we go. We're floating now in the space between atoms. The first thing you notice is the emptiness. It's like being in outer space, but stranger. The nuclei of the atoms are like distant stars, tiny points of matter separated by vast gulfs of nothing. Around each nucleus is a haze, a fog. That's the electron cloud. It's not a solid shell. It's more like, well, imagine colored smoke, drifting around a tiny lamp. That's what an electron cloud looks like. Diffuse, shifting, probabilistic. Now the finger starts to press down. We watch the atoms of the fingertip approaching the atoms of the table's surface. What do we see? The electron clouds start to get close to each other. The fogs begin to touch. And something happens. We feel it, a pressure, an invisible resistance. It's like walking into a wind that gets stronger the farther you go. The electron clouds are pushing against each other. The electromagnetic repulsion is building. And the clouds are not merging. They're compressing slightly at the edges, distorting, but there's a gap. There's always a gap. We try to push forward into the gap. We want to get to the place where finger meets table, but we can't. The pressure is too strong. The fields won't let us through. And we realize there is no contact point. There's no place where fingertip ends and table begins. There's just this zone of force, this electromagnetic battleground where clouds push against clouds. The atoms of the finger stop moving downward, not because they've hit something, but because the forces have balanced. The push from above equals the push from below. Equilibrium. And from far away, from human scale, this looks like touching. It feels like touching. But down here, we see the truth. There's a gap, a tiny gap, and nothing crosses it. Let's zoom back out now, back to the everyday world, back to the scale where tables look solid and fingers feel like they're making contact. I want you to think about what this means for everything you experience. Every sensation of touch you've ever had has been electromagnetic force. When you were a baby and grabbed your mother's finger, you didn't touch her. Your electron clouds pushed against hers. When you first held someone's hand, really held it, skin against skin, there was a gap between you that nothing could cross. Every texture you've ever felt, rough bark, smooth glass, soft fabric, all of it was electromagnetic repulsion at different scales and strengths. The roughness of bark is variations in how the electron clouds are arranged. The smoothness of glass is uniformity in those arrangements. When you pick up a coffee cup, your fingers don't contact the ceramic. They hover above it, separated by that angstrom scale gap, and electromagnetic force is strong enough to lift the weight. You're picking things up with force fields. You're living in a world of invisible telekinesis and you didn't even know it. When you type on a keyboard, your fingertips never meet the keys. They approach, the repulsion builds, the key moves down, the circuit activates, a letter appears on screen. All without contact. All through electromagnetic influence. When you feel the warmth of sunlight on your skin, that's something different. That's photons, particles of light, being absorbed by your atoms. That's actually closer to touching, in a sense. The photon is absorbed, gives up its energy, ceases to exist as a separate particle. There's a real transfer there. But even that isn't contact in the classical sense. It's an interaction, an exchange of energy, governed by quantum mechanics. Now, here's a question that might be bothering you. If we never touch anything, what about friction? What about the fact that some surfaces are slippery and others are grippy? What's going on there? Friction is fascinating. And it turns out it's still electromagnetic. When two surfaces press against each other, their electron clouds don't just push. They interact in complicated ways. The surfaces are never perfectly smooth. At the atomic level, there are hills and valleys, bumps and gaps. When you slide one surface over another, those irregularities catch on each other. But catch doesn't mean contact. It means electromagnetic interaction. The electron clouds in the bump of one surface repel the electron clouds in the bump of the other. They push sideways against each other as you try to slide. That's friction. Electromagnetic repulsion, but in the horizontal direction instead of vertical. Resistance to sliding. Rough surfaces have more bumps, more places where clouds interact. Smooth surfaces have fewer. Slippery materials have electron arrangements that don't interact as strongly. It's all electromagnetic, every bit of it. Even glue. When you stick two things together with adhesive, the glue molecules get close to the molecules of both surfaces. Their electron clouds interact, form weak bonds, electromagnetic attractions. The surfaces are held together by these interactions, but they're not touching. They're interacting through fields, through forces, through the invisible medium of electromagnetism. Let me tell you something about the forces of nature. This is one of the great stories of physics. There are, as far as we know, 4 fundamental forces. Just 4. And everything that happens in the universe happens because of them. First, there's gravity. You know gravity. It's what holds you to the earth, holds the earth to the sun, holds galaxies together. It's the weakest force by far, but it acts over enormous distances and it always attracts. There's no negative mass to push away from positive mass. Gravity just pulls. Second, there's electromagnetism. We've been talking about this one. It's what holds atoms together, makes chemistry possible, creates light, generates all the push and pull you experience in everyday life. It's much, much stronger than gravity at short distances, and it can both attract and repel, which makes it much more interesting. Third, there's the strong nuclear force. This is what holds protons and neutrons together in the nucleus. Remember how I said protons are positively charged? Well, positive repels positive. Protons should fly apart, but they don't, because the strong force is incredibly powerful at very short ranges. It overpowers the electromagnetic repulsion and holds the nucleus together. Fourth, there's the weak nuclear force. This is involved in radioactive decay in certain kinds of nuclear reactions. It's less intuitive than the others, and I won't say much about it today. Now, here's the remarkable thing. Of these 4 forces, only one of them matters for everyday human experience. Just one. Electromagnetism. Gravity matters too, of course. You'd float away without it. But gravity doesn't give you the sensation of touch. Gravity doesn't make things feel solid. Gravity doesn't create texture or resistance or the experience of holding something in your hand. All of that is electromagnetism. One force running the entire show of everyday life. The strong and weak forces are locked away inside atomic nuclei. You never feel them. They're doing important work, holding matter together at the deepest level, but they don't reach out to your experience. Electromagnetism is the one you live in, the one you swim through, the one that makes your body possible and gives you every sensation you've ever had of the physical world. And that's remarkable. That one force can create so much complexity, so much variety, the hardness of diamond and the softness of silk, the smoothness of ice and the roughness of sandpaper. All different arrangements of atoms, all interacting through the same electromagnetic force. Now I want to say something about what happens at the very smallest scales. Because you might be wondering, okay, electron clouds never touch, but what about the particles themselves? Can 2 electrons ever really touch each other? This is where things get strange. Stranger than what we've discussed so far. An electron, as far as we can tell, has no size. It's a point particle, dimensionless. Our most precise experiments have looked for the size of an electron, and we keep getting the same answer, 0, or at least smaller than we can measure. So what would it even mean for 2-point particles to touch? Points have no extent, no surface, no boundary. It's like asking whether 2 mathematical points can make contact. The question almost doesn't make sense. What we can say is that as 2 electrons get closer and closer together, the electromagnetic repulsion between them grows without limit. They're both negative. They push apart. And the closer they get, the harder they push. In practice, you'd need infinite energy to bring 2 electrons to the exact same point. So it never happens. There's always some separation. But that's using classical reasoning, and at this scale, classical reasoning breaks down. Quantum mechanics says particles don't have definite positions anyway. They're spread out in probability clouds. An electron isn't at any particular point. It's in a superposition of being at many points. So asking whether electrons touch is, in some sense, asking the wrong question. The concept of touching assumes things have definite locations and boundaries. At the quantum level, they don't. Everything is fuzzy. Everything is probabilistic. The very notion of contact becomes unclear. This is one of those places where physics gets honest with you. We don't have a perfect answer. The concept of touching just doesn't translate well to the quantum world. What we have instead are interactions, forces, exchanges of energy. Things influence each other without ever, in the classical sense, making contact. Now let's think about something that might seem troubling at first. If nothing ever touches, if there's always a gap, does that mean touch isn't real? Does it mean our experience of the physical world is somehow fake? I don't think so. And I want to explain why. Touch is absolutely real. When you feel a surface, something is really happening. Information is really traveling from the world into your nervous system. It's not an illusion in the sense of being false or deceptive, but what's happening is different from what you might naively think. You're not detecting contact, you're detecting force. Your nerve endings are sensitive to pressure. When electromagnetic repulsion pushes against your skin deforms slightly. Nerve cells detect that deformation. They send signals to your brain. Your brain interprets those signals as the sensation of touch. The whole system is built to detect force, not contact. And it works beautifully. You can tell the difference between hard and soft, rough and smooth, warm and cold. All of that information comes through. None of it requires actual contact. So touch is real in the sense that matters. It gives you accurate information about the world. It lets you navigate, manipulate objects, sense danger. Evolution built this system over hundreds of millions of years, and it works. The fact that the underlying mechanism is electromagnetic repulsion rather than direct contact doesn't make it less real. If anything, it makes it more interesting. You might even say that force is more fundamental than contact. After all, what would contact even give you that force doesn't. If two things could somehow make direct contact with no force involved, you wouldn't feel anything. There'd be nothing to detect. It's the force that carries the information. It's the force that creates the experience. So, in a deep sense, our senses are already measuring exactly the right thing. They're measuring the forces that matter. The fact that we interpret those forces as touching is just a quirk of language. The physics is working exactly as it should. Here's something else to think about. What about chemical bonds? When atoms form molecules, they share electrons or transfer electrons from one to another. This creates bonds, connections between atoms that hold molecules together. When you look at the structure of water, for instance, you see oxygen and hydrogen atoms bonded together. Are those atoms touching? No, they're still not touching. What's happening is that their electron clouds are overlapping in specific ways, sharing certain electrons, creating a configuration that has lower energy than the atoms would have separately. The bond is an electromagnetic arrangement, a particular organization of charge that keeps the atoms at a certain distance. Not too close, because the repulsion would be too strong. Not too far, because the attraction would weaken. A balance. The atoms in a molecule are held together by forces, not by contact. They're like dancers holding hands, but not quite touching, connected by the invisible grip of electromagnetism. And when you break a chemical bond, when you tear a molecule apart, you're not separating things that were in contact. You're overcoming an electromagnetic attraction. You're putting in energy to change the arrangement of electron clouds. This is true even for the bonds in your own body, the proteins in your muscles, the DNA in your cells, all held together by electromagnetic forces, all made of atoms that have never touched. You are, in a very real sense, a sculpture made of force fields, a pattern of electromagnetic interactions, holding itself together, walking around, thinking about physics. Now let me push this a bit further. What about when things break, when you snap a twig or crack a piece of glass? We usually think of breaking as separating things that were joined. But what's really happening? The atoms in a solid are arranged in a structure, a crystal lattice in the case of glass or metal. Each atom is held in place by electromagnetic forces from its neighbors. The structure is stable because all those forces balance out. When you put stress on the material, you're pulling atoms away from their neighbors. The electromagnetic bonds stretch. The forces increase. If you pull hard enough, the forces exceed what the bonds can handle. The arrangement fails. Atoms slip past each other or separate entirely. The material breaks, but nothing was ever in contact. What broke was an electromagnetic configuration, a pattern of forces that held things together and then couldn't hold anymore. This is why understanding atoms as fields rather than balls matters. If atoms were balls, breakage would be about those balls moving apart. But atoms are clouds, and breakage is about force configurations changing. The same is true of melting. When ice turns to water, the electromagnetic arrangement changes. The atoms don't touch and then stop touching. They rearrange from one force configuration to another. Everything is force configurations, all the way down. Let me talk about something practical now. What about when things heat up? Temperature at the atomic level is motion. The hotter something is, the more its atoms are jiggling, vibrating, moving around. In a solid, they vibrate in place. In a liquid, they slide past each other. In a gas, they fly freely. When you touch something hot, what's happening is that the atoms in the hot object are vibrating intensely. When your skin gets close, those vibrating atoms push harder against your electron clouds. The repulsion fluctuates rapidly. Energy transfers from the hot object to your skin through these electromagnetic interactions. Your atoms start vibrating more too. That's what heating up means. Your nerves detect the change and interpret it as heat. But again, no contact. The energy transfer happens through electromagnetic forces. The hot atoms push against your atoms, and the push carries energy. It's like if I had two tuning forks, and I hit one and held it near the other, the second one starts vibrating. Not because they're touching, but because the sound waves in the air transfer energy between them, except at the atomic level, there's no air needed. The electromagnetic field itself carries the vibration. This is also why insulators work. Materials like wool or foam have lots of air pockets. Air is thin at the atomic level. Fewer atoms mean fewer electron clouds to transmit vibrations. Energy has a harder time flowing. So the insulator reduces heat transfer, not by preventing contact, because there was never contact to prevent, by reducing the density of electromagnetic interactions. Now, I've been talking about what we know, but let me be honest about what we don't know. We have excellent theories of electromagnetism and quantum mechanics. They've been tested more precisely than almost anything in science. They work. They predict what happens in experiments. They let us build computers and lasers and all the technology around you. But there are still deep questions we can't fully answer. Why does the electromagnetic force have the strength it has? Why is the electron's charge exactly what it is? These numbers seem arbitrary. We don't know where they come from. What is an electron, really? We describe it as a point particle, but what does that mean? How can something with no size have mass and charge? We have mathematics that works, but the picture it paints is strange. Why does the Pauli exclusion principle exist? We know it works. We know it's connected to the spin of particles, to the mathematics of identical particles. But why should identical fermions refuse to share states? What enforces this rule? These are open questions. Active research. I don't want to pretend we've got everything figured out, because we don't. Science is honest about its limits. But what we do know is remarkable. We know that everything you've ever touched has been an electromagnetic interaction. We know that atoms are mostly empty space. We know that electron clouds repel and that quantum mechanics forbids certain configurations. We know enough to understand why the world feels solid even though it isn't. And that understanding, even if incomplete, even if there's more to learn, changes how you see things. Let me bring this home. You've spent your whole life in a world of force fields. Every handshake, every kiss, every time you've caught a ball or climbed a stair or felt rain on your face, all electromagnetic, all forces acting across gaps that never close. And here's the beautiful thing, it doesn't make any of that less real. It makes it more profound. Because what this tells you is that interaction is fundamental. Connection doesn't require contact. You can influence something, be influenced by something, without ever merging with it. In fact, maybe that's a better way to think about relationships in general. We're all separate. Our atoms never mix. But we push against each other, exchange energy, change each other's configurations. We interact through fields, through forces that reach across the gap. That's what connection is. Not the absence of separation, but interaction across it. The universe is made of particles and forces. Particles are the stuff. Forces are how the stuff relates. And the relating, the interacting, is what creates everything you experience. When you feel the ground beneath your feet, that's the electromagnetic force telling you that you're supported, that you won't fall through the earth, that the planet is here, under you, holding you up. When you hug someone, that's electron clouds refusing to merge, but refusing gently, pushing back just enough to say, I'm here, you're here, we're close. This is as close as anything gets. And maybe that's enough. Maybe that's more than enough. The universe didn't have to give us any sensation at all. We could have been ghosts, drifting through matter, feeling nothing. But instead, electromagnetism creates this rich world of texture and pressure and warmth. It lets us feel like we're part of things, like we're in contact with the world. We're not, technically. But the experience is real. The connection is real. The force is real. And that's what I want to leave you with. You've never touched anything, and you never will, but you've felt the electromagnetic force of everything you ever thought you touched. That force is real. It's physical. It carries information and energy. It connects you to every object you've ever held. You are embedded in a web of electromagnetic interactions, constantly sensing the world through the push and pull of fields. And that web is what makes you part of the physical universe. Not contact, interaction, not touching, relating. I think that's beautiful. I think it changes how you should see the world. Not as a collection of solid objects bumping against each other, but as a dance of fields, a symphony of forces, a universe where everything influences everything else across gaps that never close. Now, I have a question for you. Knowing that you've never truly touched anything, does that change how you think about your experience of the physical world? Does it make things feel less solid or more wondrous? I really want to know what you think, so tell me in the comments.